say that a complex number lambda is said to be an eigenvalue of t. So here we are always talking about only for week 5 we are only concerned about transformations from R2 to R2. Okay, or if there are any changes, in that case we will be specifically mentioning. So we are particularly now talking about t from R2 to R2. So now for this, what is an eigenvalue? So a lambda is called an eigenvalue if we have t minus lambda is singular. What is meant by t minus lambda is singular? This means it is non-invertible. So if this is non-invertible, then the corresponding matrix representation, which is a minus lambda I, will have determinant 0. Okay, so this means what? The eigenvalues of a matrix A. So the matrix, so here A is nothing but the matrix of T. Okay, so if you have T, then the eigenvalues of T are same as the eigenvalues of A. Okay, and how are we finding the eigenvalues of T? By calculating the solutions for determinant of A minus lambda I equal to 0. Okay, now what are eigenvectors? Suppose lambda is an eigenvalue of an operator t, then the null space t minus lambda I is called the eigenspace of t with eigenvalue lambda. So here only we consider non-zero vectors when we are looking at eigenvectors. Eigenvector is always non-zero. So all non-zero vectors in the eigenspace is called are called eigenvectors. Okay. So since we know that there is at least one non-zero eigenvector, so null space of t minus lambda I is non-zero because determinant is 0. This null space is non-zero. So this null space is non-zero means the dimension is at least 1, right? So it has non-zero eigenvectors, so the dimension is at least 1. Okay, so in other words, if there is a non-zero vector v such that t v equal to lambda v, we say that lambda is an eigenvalue of t with eigenvector v. Okay, so here an important note is that if lambda is equal to 0, if lambda equal to 0, then what is the eigenspace corresponding to lambda equal to 0? What are the eigenvectors?
Equal to
The eigenvectors
two,
corresponding to lambda equal to 0 are nothing but
equal to null space.
are the non-zero vectors in the null space. You have to be careful. Are the non-zero vectors in null of t. Okay, this is something we should remember. Okay, fine. Now let us see whether you have understood and tried it. So here we have a very simple question. So find the eigenvalues of find the eigenvalues and eigenvectors. Everyone do it. Take your paper and pen. Quickly do it. First of all, what is the matrix representation?
1102.
1012.
Row.
Okay. So now, is it a triangular matrix?
Yes, ma'am. It is upper triangular matrix.
So what is lambda 1 and what is lambda 2?
Lambda equal to 1
One.
and 2.
Yeah. Okay. So now we need to find the eigenvectors corresponding to 1 and 2. Okay. So AV1 equal to lambda 1 V1 gives you what? So you have 1 minus 1. So it is same as saying A minus lambda 1 I times of V1 equal to 0. Right? So 1 minus 1, 1, 0, 2 minus 1 times of xy equal to 0, 0. What does this give you? 0.
Y is equals to 0.
Yeah. So you get y is equal to 0. So this implies y is equal to 0. So we can take v1 to be 1 comma 0. Can you find v2 in the same way? Right? A minus lambda 2I v2 equal to 0. Solve it and find what is v2. What can be v2? V2 can take several different values. So give me one vector which satisfies this condition.
V2 will be 0, 1. X will be 0 and y can take any values.
Are you sure?
It is minus x plus y is equals to 0.
Yeah. So here you see a minus lambda 2I is a minus 2I. So here you will have minus 1, 1, 0 and 0 times of xy. Right? So this means it is minus x plus y. The equation you get here is minus x plus y equal to 0, which means x is equal to y. So for example, I can take v2 as 1 comma 1. Yeah, all right.
Yes, ma'am.
Okay. So what is that we observe? What do you observe about v1 and v2? First of all, these are real and distinct roots. Right? What is mean by distinct? Lambda 1 is not equal to lambda 2. Distinct means what? They are not equal. Now, what do you observe about v1 and v2? Yes, Sonali.
Ma'am, in the first vectors, we don't have any equations of the x. So how do we consider here 1 for x?
Yes. So now here, what do we get? We get, so from this, the solution is set of all x comma y such that y is equal to 0. This is what we have obtained. Now, why we are taking x is equal to 1? There is no such rule that we have to take x is equal to 1, because here you see this can be rewritten as set of all x comma 0 such that x is in R, which is just span of 1 comma 0. So v1 can be any non-zero vector of the form x comma 0. That's all. Got it?
Yes, ma'am. So any value of the v1 is possible for v1.
Yeah, just it has to be non-zero. Similarly here, why did we take 1 comma 1? Just for simplicity, you can choose any value, 2 comma 2, 0.5 comma zero point 0.5, anything you can take which is that will satisfy this equation is an eigenvector. Okay, we are choosing something which is simpler for us. That's all. Okay,
Okay, ma'am.
all right. Okay, now what is that you observe about v1 and v2? V1 and v2 are
Distinct.
Linearly independent.
linearly independent. Okay, so we note that lambda 1 not equal to lambda 2 and v1 and v2 are linearly independent. Okay, this is an important observation. Similarly, let's look at this one, and another important observation is also here. Now eigenvalues are lambda 1 is non-zero, lambda 2 is also non-zero. So we have one, so all eigenvalues of A are non-zero, right? So if all eigenvalues of A are non-zero, what can you say about determinant of A? Can you quickly compute the determinant in this case? What is the determinant?
2.
2.
And also, can you observe that the determinant is lambda 1 into lambda 2? Yes?
Yes, ma'am.
Okay. Another observation is that, do you all recall what is mean by trace of a matrix?
Sum of diagonal elements.
Yeah. So what is the sum of diagonal elements in this case?
3.
3.
3. And what is The sum of eigenvalues.
3.
Okay, so is it a coincidence because it is a triangular matrix? Let's see whether it is a coincidence or is it a fact. Okay, fine. So non-zero eigenvalues imply A is, or if and only if A is invertible. Okay, fine. Now what is the matrix here? In this,
1, 3, and 2, 6. Ma'am, not like this. I told it in row.
so it should be 1, 2, and 3,
3,
6.
6.
Right? All right. Now, what are the eigenvalues?
Uh,
Yes, Shonali. What's your question? Okay. Yeah. So, what are the eigenvalues for this matrix? Can you compute and tell me?
0 and 7.
0 and 7.
7.
Okay. So, lambda 1 is 0, lambda 2 equal to 7. Also, can you find V1 and V2?
Excuse me, one question, please.
Yes, yes.
Can we do the row reduction for finding out eigenvalues, or is that not allowed?
Row reduction does not make sense to find eigenvalues. No,
We can't do that.
no, no.
Okay.
Ma'am, for V1, both are 0.
As I told
Except
you, you should never take V eigenvectors as zero vectors.
Ma'am, V1 should can take minus 3 and comma 1.
Okay. So V1 is minus 3 comma 1. Okay. What about V2?
Ma'am, 2 comma 1.
1 comma 2 or 2 comma 1?
2 comma 1.
Are you sure? Can you check?
Okay, let me, ma'am. Ma'am, 1 comma 2. Sorry.
Yeah. Okay. Fine. So now what is that you observe? So again, this is now not a triangular matrix. Now what is the determinant?
0.
0.
0. Right? Again, it is lambda 1 into lambda 2. So what is that we see? A is singular if and only if A has a 0 eigenvalue. Okay. And also here, what is the trace?
7.
7.
7, which is lambda 1 plus lambda 2. Correct? Okay. And also here again, V1 and V2, are they linearly independent? Are they linearly independent?
Yes.
Yes, ma'am.
Okay. So V1 and V2 are linearly independent. Okay. Good. So here again, lambda 1 is not equal to lambda 2, and V1 and V2 are linearly independent. Okay, so this forms actually a basis for entire R2, but also can you note that V1 forms a basis for Can you complete? For
The
which
null
I2.
space.
the null of T. And V2 forms a basis for basis for
Row space, is it?
no
Range.
range. Obviously column space 1 2, right? For row it is 1 3. For column it is 1 2. Remember range is the column space, right? Okay, so these are some important observations. Okay, and V1 and V2.
Excuse me.
Yes.
Sorry, is this coincidental or?
These are none of these are coincidental. Okay, so now I have just given in some examples to like visualize the properties before we are just stating them. Okay, so in general, eigenvectors of distinct eigenvalues are linearly independent. Okay, so it means what? Suppose you are having T from R2 to R2. Okay, and you have two eigenvalues lambda 1 and lambda 2 which are distinct. So what does this means? So this means that the eigenvalues are distinct. So or maybe I'll write distinct eigenvalues. Okay, so if we are having distinct eigenvalues, then the corresponding eigenvectors v1 and v2 are linearly independent. This is what is the statement. Now, how can we see this? Here is a simple proof. So, how do you prove linear independence of any two vectors? Either you see whether they are multiple of each other, or the usual definition. This is how you prove, right? So, you take AV1 plus BV2 equal to 0, then you show that A equal to 0 and B equal to 0. This is the usual definition. Yes? Okay. So, let's start here. So, let AV1 plus BV2 is equal to 0. Now I am going to apply T. So T of AV1 plus BV2 is A times of TV1 plus B times of TV2. So this means what? TV1 is now lambda 1 V1 and TV2 is lambda 2 V2. Okay. So now this you know that it is equal to 0 because this is 0. So T of this is also equal to 0. Okay. Now what I am doing, so let's call this equation 1. Okay, so I'm going to multiply lambda 2 equation 1. Okay, so this is what I'm getting. So maybe let's call this equation 2. Now this is equation 3. Now can you tell what you get if you subtract 2 and 3? What is 2 minus 3? What are the common terms? B2 lambda 2 V2, B2 lambda 2 V2 will get cancelled. So what will be remaining?
A lambda 1 v1 minus a lambda 2 v1.
Can I write it in this way?
Yes, ma'am.
Okay, so now we know that lambda 1 minus lambda and lambda 2 are not equal. So this means that lambda 1 minus lambda 2 is non-zero. Also we know that v1 is non-zero. So this means
A
what
is
should be
0.
0? A is 0. Okay, now can you tell me, from this you should already have an idea how to make b as 0. How will we make b as 0?
We can multiply by 3 with lambda 1 and subtract 2 and 4th
Yeah, so
equation we
we
get.
multiply lambda 1 with 1, good. So here you will get a1 lambda, sorry, a lambda 1 v1 plus b lambda 1 v1, v2 equal to 0. So now this is, let's call this equation 4. Now you do 2 minus 4. What will you get? So the first term is common. A lambda 1 v1, a lambda 1 v1 is common. So they will get cancelled out. So what will be left?
B
We
comma.
have, again you know that lambda 2 minus lambda 1 is non-zero and v2 is non-zero. So these two are non-zero. So this should imply
B is 0.
b is 0. So a is 0, b is 0 will imply v1 and v2 are linearly
Nearly independent.
independent. Okay.
Ma'am, I had one question in the earlier
Yes,
that
yes.
in that we got matrix determinant as 0. So in this type of questions, we can't say that if a matrix determinant is 0, so they are linearly dependent. So
No,
it's not
no.
works
See,
like that,
that's not
right?
that's why I took this specific example. Students tend to confuse, like even if lambda 1 is not equal to lambda 2, if there is a zero eigenvalue, they have a doubt. That's why I took this specific example. See, the only property you need is that you need distinct eigenvalues. Whether it is zero or non-zero does not matter. As long as your eigenvalues are distinct, the corresponding eigenvectors are linearly independent.
Okay,
Okay.
ma'am, got it.
So here, I hope this proof is clear for everyone that how to see whether two linearly independent vectors corresponding to distinct eigenvalues are linearly independent. How to prove that? This is the simple proof. Okay, I hope this is clear. So there are other properties which we have already mentioned. I have put it here. If matrix is singular, then one of the eigenvalues is zero. This is also something we noticed in the example, right? And if it is invertible, then the corresponding eigenvalues are non-zero. From where these two properties come? This two property comes from here. So the product of eigenvalues, maybe I'll write product of eigenvalues is the determinant of m of t. So since the product is so determinant of m of t is nothing but lambda 1 lambda 2, right? So from here, if this is 0, then one of this has to be 0, and if this is non-zero, then both of them has to be non-zero. So you see that these two properties are just a result from this main property, that the determinant is the product of eigenvalues. Okay. And also the trace, which is the sum of diagonal elements, is the product of eigenvalues. Okay. So these are some important properties which we should notice. Okay. There is something more which we have to check. Not check, maybe we have to note, I should say. What is the characteristic polynomial? Characteristic polynomial, the word we have not used. So what is a minus lambda I in this case? In this case, can you tell me what is determinant of, maybe I should write it here. What is determinant of a minus lambda I in this case?
Ma'am, which lambda? Lambda 1 and 2?
No, just the
Just
variable lambda. So what is this?
Zero.
Lambda square,
Lambda is equals to
lambda square, and then
lambda is equals to 1 or 2.
minus 3 lambda. No, I want this polynomial equation, quadratic equation. And then you have here plus 2 and then plus 1. So it is
Plus
plus
lambda square.
uh,
Plus 2,
plus
ma'am.
plus 2.
2.
okay, it's just plus 2. All right. Now, one thing you have to note here is that, so what is this 3? This 3 is the trace of
Trace.
A, and this 3 is the determinant of A. Or otherwise, you can say this 3 is the sum of the eigenvalues and this 2 is the product of the eigenvalues. Okay. Can you see the same, do the same observation here also? So determinant of A minus lambda I is 1 minus lambda 3 2 6 minus lambda. So lambda square, and then you have minus 7 lambda, and then you have plus 6 and minus 6, so it becomes 0. Only this you have. So lambda into lambda minus 7, right? So here you see that now what is the coefficient here? The coefficient here, maybe I will put it as plus 0. Okay. So here you again can see that this is nothing. So not the negative part. You should not take the minus. So without the minus, only this. This is the trace of A, and this is the determinant of A. Is that clear?
Yes, ma'am.
Yeah.
Excuse me.
Yes.
I'm reminded of
Yes.
something we studied in class 10th about the quadratics. You know that if you have a general quadratic ax square plus bx plus c, then
Hmm.
the sum of the roots you can find out by doing minus b by a, and then you can do product of the roots, and that will be c by a. It's looking like exactly the same thing here.
Yes, yes, exactly the same thing. We are checking here also. We are
I'm
observing here also. Only thing I
just
show that just let me complete the statement. So here the sum is also the sum of eigenvalues, and the product is also the product of eigenvalues. And the determinant is also the product of eigenvalues. Yes, continue.
I'm just like class 12 matrix characteristic equation we are studying, right?
This is the characteristic. Yes, exactly. This is a
Yeah.
characteristic equation. Yeah. Okay. Good. Okay. So another
Also,
thing.
one question I had, one
Yeah,
more
yes,
question, please.
yes, yes.
Uh, we saw here in this example that the eigenvectors were correspondingly the basis of the null space and the range. The null
Yes.
space part I get because one of the eigenvalues is 0. Now the
Hmm.
other one,
Hmm.
the basis for the range, is
Hmm.
this uh, is this because A turned out to be singular, or this has some other implication? Could you please elaborate?
So this is because of the definition of eigenvalues and eigenvectors. What is the definition? We have TV2 is equal to lambda 2 V2, right? And you know that, so V1 and V2 are linearly independent. And what is range of T? The definition, set of all V such TV such that V is in R2, right? So this I can say it as span of TV1 comma TV2, right? Because V1 and V2 are linearly independent. But what is TV1? What is TV1? TV1 is,
TV1 is 0.
so this means it is just left with TV2, and TV2 is nothing but lambda 2 V2. So lambda 2 V2 or V2 does not make any difference, right? Span of lambda 2 V2 is same as span of V2. So now do you see why V2 is a basis for range of T? Yeah.
I'm sorry, still not entirely clear because uh, we are just saying for t of v2, right? But if we take t of something else instead of v2, we take some random v, then will it still land up in v2 itself?
That is what I'm saying. Here, see, what is TV? TV, I know that V1 and V2 are linearly independent. Yes or no?
Ah,
So
that
this is,
much is seen.
yes. So this means that this forms a basis for R2. Yes or no?
Entire domain is covered by these two.
Yes. Okay. So now this means what? Now the range definition is set of all TV such that V is in R2. Yeah. So now can I write my V as alpha V1 plus beta V2 because of this?
Because we have entire coverage of the domain through v1
Yes.
and v2.
Yes. Can we do that?
Ah, we can do that.
Yes. In that case, now what is TV? TV is nothing but alpha TV1 plus beta TV2, which is same as beta TV2 because TV1 is 0, right? And beta TV2 is nothing but
Beta
lambda to
lambda
V2.
v2.
So it is just a multiple. It is just a multiple of V2, right? So this belongs to span of V2. Is that clear now? That
So
any,
that
yeah.
so this happens because a is singular, correct? No, otherwise v1 would not go away.
See, the thing is that what is that you need to observe is that the non-zero the eigenvectors corresponding to the non-zero eigenvalues here in this case is spanning the range, and in this case the eigenvectors corresponding to the non-zero eigenvalue is again spanning the range. Okay, so as you move on, we will see maybe in week 7 and 8 you can have like 3 by 3 matrix and all. So in that case what will happen, I will tell you. So for example, let us say you have 3 eigenvalues for a 3 by 3 matrix. Okay, so let us say you have lambda 1, lambda 2, lambda 3. Okay, now all are, let's say, distinct, and suppose one of this is something like, suppose we have these are the eigenvalues, let us say. Okay, now in this case, let's say v1, v2, v3. In this case, what will happen? These two will span range or form a basis for range, and this will span null. This is what will happen when they are distinct. Okay. Okay, so are you able to see what's going on? What is the norm?
Now I think I get it. As
Okay,
long as we have distinct eigenvalues, the eigenvectors will span the entire domain. And
exactly,
when we span the entire domain, we can split it up into the null space and
yeah,
uh, the range itself in that
exactly,
sense.
exactly. Okay,
Because of the rank nullity theorem, they will get divided in that way.
yeah, mainly because of that, and also this, that the vectors are linearly independent. Because of that property only, we are having this spanning property. Okay, without linear independence, we cannot have that, right? We need linear independence. Okay, fine. Shall we
Okay.
proceed? Okay. All right. So, what are the important properties we have seen? The first one is that eigenvectors of distinct eigenvalues are linearly independent. And then, if determinant is equal to product of eigenvalues and trace is equal to the sum of eigenvalues, and because of this, the matrix is singular if and only if you have a zero eigenvalue, and invertible if and only if all eigenvalues are non-zero. Okay. So these are some important properties. Now, this is a very straightforward question.
Sorry,
Yes.
one more thing.
Yes.
The proof you had shown for us to know the linear independence, I
Hmm.
feel that we can do it in another way, as in we can take this a v1 plus b v2, and then we can make a matrix out of v1 and v2 being the columns of that matrix, and then we will attempt to find the null space of that matrix. No, so it will be like v1 v2 are the columns of the matrix, and we are multiplying the ab vector, and we are trying to find the null space, and we have to show that the null space only has the origin. That will also imply that v1 and v2 are linearly independent. Does that also work?
That is the usual depiction of any linear combination. So a linear combination. So in fact, system of linear equation, solving system of linear equation can be also viewed as a linear combination problem. So both are equivalent. So that is something which we have seen in the beginning weeks. Yes, you are correct. Okay, fine. Okay, so now looking at this example exercise, just read this and tell me what are the correct options.
Option A is correct.
Okay, so obviously B is incorrect. What about option C? So this will mean that they are linearly dependent, right? So again, this is incorrect. So can we say that just because the eigenvectors or eigenvalues are distinct, can we say that one of them must be zero?
Yes, ma'am. This may be correct.
See, no. See, we also have seen it is possible, right? The eigenvalues are 1 and 2. It need not be always 0. So if they are saying if 0 may be an eigenvalue, then it is fine. But they are saying 0 is an eigenvalue. They are saying should be. Then that is not correct, right?
Yes,
Yeah?
ma'am. Yes,
Okay.
ma'am.
Okay. All right. So based on the properties which we have seen earlier, try to answer this question. What about exercise 12? Consider a matrix
4.
A. Okay. So here trace should be sum of the eigenvalues. So minus 1 plus 5, 4. Okay. Let A be the matrix such that the 2 and 4 are the eigenvalues. What should be the determinant?
8.
Okay. Good.
One question about the symbol above, please. This symbol for showing that 0 is not part of the real number set. Is this backslash a common symbol, or
Oh,
Ma'am, option third.
okay. So this one Here this set, we call it set minus, but we usually want to the name, this is called set minus, but usually this is just saying the set of all non-zero real numbers. So this is not just a notation only here. In general, this set minus can be used in many places. Suppose you want to include a set of numbers from another set, then you can use this set minus symbol. Okay. Here we are talking about set of non-zero real numbers.
And we can also put multiple things on the right hand side of the set minus, or
Exactly.
just one thing we can.
Exactly. Yes, we can do that. So, for example, if you have A is a real number and B is maybe I want all the negative integers, maybe or just a Z, the integer set of all integers. Okay, this makes sense. So, I am considering all real numbers which are not integers, A minus Z. Okay, so this definition is valid with the set minus. This is a set minus. Okay, fine.
Okay, thank you.
Yeah. All right. So the next thing, we are moving to a very important property of eigenvalue, which are what is the algebraic and geometric multiplicity. Before looking at the definition, let's again go back to the examples we have seen. Okay, so the examples I did not do it today. It was from yesterday. So let me write them here. Okay, so let me consider um, how many different scenarios, all the three different scenarios which we did yesterday. So case 1, okay, lambda 1, lambda 2, they are real and distinct. So this means that, for example, lambda 1 is equal to 1, lambda 2 is equal to 2. Okay, so now you see that how many times are we getting 1 as an eigenvalue for A? It is repeating only once. Similarly, 2 is repeating only once. But when we are considering a repeated eigenvalue, so for example, let us say lambda 1 and lambda 2, they are real and repeated. So this means what? Both lambda 1 and lambda 2 are taking the same value. For example, if it is 1, then how many times my 1 is getting repeated?
2 times.
2 times. So here, what is meant by algebraic multiplicity? Algebraic multiplicity of an eigenvalue is the number of time it is repeating as an eigenvalue of that specific matrix. Okay, so for example, lambda 1 is repeating only once here, so it is 1. And algebraic multiplicity of lambda 2 is 2.
1.
Sorry, again 1. It is again 1. But what about algebraic multiplicity of lambda equal to 1 here?
2.
It is 2 because it is repeating twice. Okay. Now the case 3, which is the lambda 1, lambda 2. What is the case 3? Can anyone remember?
One of them is
Complex
Complex
conjugate.
groups,
Yes.
complex conjugates.
Complex conjugate pairs. Right? So in that case, so you obviously know that, so if lambda 1 is, for example, 1 plus I, lambda 2 is 1 minus I, then what can you say about the algebraic and geometric multiplicity? First, let's talk about algebraic multiplicity. What is algebraic multiplicity? How many times 1 plus I is repeating?
once.
So again, here also it is 1. Okay, fine. Now let us consider a specific matrix. So these cases, it is quite like straightforward. But what about this case is what we are going to see. This is a special case. So let us consider A is equal to 1, 1, 1, 1, or maybe 1, 1, 1, 0. Now in this case, you know that it is a triangular matrix. So lambda 1 equal to lambda 2 equal to 1. Right? So now find the eigenvectors corresponding to lambda equal to 1. Can you please quickly do this? What are the eigenvectors corresponding to eigenvalue 1?
Y is equals to 0.
Okay, so are there any other eigenvalues?
No, ma'am.
Okay, so in that case, you are getting only one linearly independent matrix, right? Sorry, vector. So let me write it. So here you are having, so a minus lambda I v equal to 0 implies, so 0 1 0 0 xy equal to 0 0. So this will mean that your y is equal to 0. So you have only one eigenvector. So so here in this case you are having only one linearly independent eigenvector
Sorry, 1 comma 0.
for lambda equal to, oh sorry, yeah, only one linearly independent vector for lambda is equal to 1, right? So now here already this scenario we know, for lambda 1 equal to 1, how many linearly independent eigenvectors do we get?
Can you repeat your question again?
Just a moment, can you hold on? Yeah, sorry. So the question is that corresponding to lambda 1 equal to 1, how many linearly independent eigenvectors can you find?
One.
1, right? So here the geometric multiplicity is the number of linearly independent vectors corresponding to that particular eigenvalue. So it is 1. So whenever you have real and distinct cases, in that case the geometric multiplicity will obviously be 1. Okay, but in this case, now what is the geometric multiplicity? What is the geometric multiplicity? How many linearly independent eigenvectors are here?
1.
You are having 1. So now in this case, you see that the algebraic multiplicity is 2, but the geometric multiplicity is 1. They are not equal. Okay, so in the previous cases we see that the geometric multiplicity and algebraic multiplicity are equal in both these cases, but in this case the algebraic multiplicity is not equal to the geometric multiplicity, which has a significant impact on the matrix. Okay, and similarly in this case also, since they are distinct, here also we will have geometric multiplicity of lambda 1 is equal to 1, and geometric multiplicity of lambda 2 is 1. Yes, what's your question?
And also, can we say that whenever we have a algebraic multiplicity, S2 means there would be dependent vectors, so geometric multiplicity would always be 1.
No. So there are cases where you have algebraic multiplicity is 2, but still the geometric multiplicity is also 2. That is also possible. Okay. So
Okay.
for example, consider this matrix. Where I have.
And when it would be not upper triangular.
Yeah, for example, take the identity matrix itself. Okay. So let's take the identity matrix. So if your A is 1 0 0 1. Now in this case, What can you say about lambda 1 and lambda 2? You know both are 1. Now, what are the eigenvectors?
1 1.
No. Please be careful. What are the eigenvectors?
Uh, Ma'am, both will be not 0. Like we can take anything.
Yes, we can take anything. So it means what? We have two variables, both of which are linearly independent, right? So in that case, so here you see that here you have two linearly independent vectors. So you can maybe choose 1 0 0 1 itself. So v1 I can take 1 0. So this is the random choice I'm doing. You can take any two linearly independent vectors. So you can see that a v1 is equal to v1 and a v2 is equal to v2, right? They are linearly independent. So here in this case you see that algebraic multiplicity of lambda equal to 1 is same as geometric multiplicity of lambda, which is 2. Okay, fine. So what is algebraic multiplicity and what is geometric multiplicity? Is that clear? Let's
Yes,
see,
ma'am.
let's see the definition now. If lambda is an eigenvalue of a matrix, the algebraic multiplicity of lambda is the number of times lambda appears as a root of determinant of a minus lambda I. So whenever we are having real and distinct roots, so each of this eigenvalue will have algebraic multiplicity 1. In the case when we have repeated eigenvalues, in that case the algebraic multiplicity is 2. In the case of complex eigen conjugate solutions, again you have algebraic multiplicity 1. And the important thing you should note is that sum of the algebraic multiplicity of distinct eigenvalues is 2. So here you see in any case the sum is 1. Here together we have 2. Here also 2. In any case it is 2. Okay. And for an eigenvalue lambda, the dimension of the null space. So here the dimension of null space of t minus lambda I. This is called the geometric multiplicity of lambda. In other words, so the other term which we have used here is number of linearly independent eigenvectors for lambda. So that is the geometric multiplicity of lambda. Okay, and this is very very important. I will put it in red. Okay, so this is very very important, this note. Okay, always the geometric multiplicity is greater than 1, greater than or equal to 1. Okay, and it is less than or equal to 2 for t from r2 to r2. Okay, in general you have 1 less equal to geometric multiplicity less equal to algebraic multiplicity. This is the usual rule. And algebraic multiplicity, for suppose you have a is an n by n matrix, then your algebraic multiplicity is less than or equal to n. Okay, so this is the general rule you have. Remember this is very important. Okay, now based on the information we have, can you try to answer this question? Go through it carefully. So to answer about geometric multiplicity, you need to calculate the number of linearly independent eigenvectors. So it means you need to calculate the eigenvectors for this matrix. Calculate the eigenvectors.
Ma'am, B option.
Okay, what are the eigenvalues first of all?
Sorry, ma'am.
Eigenvalue 3. Lambda.
Okay, and the algebraic multiplicity is 2 because it is repeating twice. Okay.
Third option is also correct.
I think geometric multiplicity is 2.
Okay, so let's check. So a minus lambda I times of v equal to 0 gives us 0 1 0 0 xy times of 0 0. So this means your y is 0. So again you have v is 1 comma 0. So geometric multiplicity is just 1. Only one linearly independent eigenvector.
Okay, ma'am. I did one thing wrong.
Yeah. Okay, so this does not, so this is another important thing we should note. Okay, so note that here range is not spanned by eigenvectors. Okay, so when you don't have algebraic multiplicity and geometric multiplicity, if they are not equal, then the range cannot be spanned by eigenvectors. Okay, so you can observe that in this scenario also. So here also you see that only one linearly independent eigenvectors and both are non-zero eigenvalues, but still the range cannot be spanned by the eigenvectors because the algebraic multiplicity is not equal to the geometric multiplicity. Okay, so this is something important you should observe. Okay, range is not spanned by eigenvectors. Okay, fine. Okay, now
Excuse me.
yes.
If if some matrix has eigenvalues which are only complex, so
Hmm.
in that case we will always have distinct eigenvalues, right? Because the complex roots will be conjugates of each other
For 2
for
by
each
2
one.
case, for 2 by 2 case, yes, but for general scenario, it need not be. Right?
As
We
in the
can,
complex roots can also repeat. Is that how it is?
yes. For n by n case, the complex conjugate can repeat. Okay. So, for example, imagine you have a matrix like this. So, yesterday, what was the example we saw? The example we saw was 0 1 1 0. This was the example where we had complex root, if I am correct. Yes. Now, suppose, let's say you have a matrix like this. What do you think are the eigenvalues? It's going to be I minus I, I minus I. Okay?
Twice repeated for each one.
Yes. For this 4 cross 4 matrix. So this we will see in week 7, I guess. Okay? So this for 2 by 2, yes, if we have complex numbers as eigenvalues, then the algebraic and geometric multiplicities, they are equal. But in general scenarios, we do not know. It need not be equal. Okay? Fine.
Also, I'm having some trouble understanding that one line you wrote in red.
This one?
That one.
Okay, so this one, okay, see, always, so let us say you are having only one eigenvalue. Mm, So you are having only one eigenvalue, one distinct eigenvalue, suppose you are having. So in that case, you obviously see that you can have only one linearly independent eigenvector. So this means what? The algebraic multiplicity is unbound for your geometric multiplicity. You cannot have more number of eigenvectors than the number of times the eigenvalue is getting repeated. Okay. So for example, here you are having the eigenvalues is repeating twice, so your geometric multiplicity cannot exceed the algebraic multiplicity. Okay, that is the first thing you should know, that the algebraic multiplicity is always an upper bound for the geometric multiplicity. And geometric multiplicity is always 1 because what do we know? We know that dimension of null of t minus lambda I is at least 1. This is something we at least know. And this is what is geometric multiplicity. And the first equality comes from this. Okay, and the second one is because algebraic multiplicity is always the upper bound for geometric multiplicity. And the last one here is that, see, for an n by n matrix, determinant of a minus lambda I is a polynomial, nth degree polynomial. It's a nth degree polynomial. So for an nth degree polynomial, how many distinct roots can it have? Maximum number of distinct roots?
N.
Yes. So maximum n roots, n distinct roots. So the algebraic multiplicity cannot exceed n. Is that clear now? Yes.
Also, how were we defining this algebraic multiplicity? Can you please go over that again?
Algebraic multiplicity is simply the number of times you are getting lambda as a root for determinant of a minus lambda I, or in other terms, the number of times lambda appears as an eigenvalue of a. Okay, so for example, let us say you are having a 5 cross 5 matrix where the eigenvalues are 2, 2, 2, and 3, 3. Now, what is the algebraic multiplicity of lambda is equal to 2? How many times it is repeating as an eigenvalue?
3.
3. Okay, and what is the algebraic multiplicity for lambda is equal to 3?
2.
Do you understand now?
Sorry, one thing I was missing here that just became clear. So it is defined per eigenvalue. Both these terms,
Yes,
algebraic multiplicity and geometric multiplicity, are defined per eigenvalue and not for the whole matrix.
correct.
Okay, okay, thank you.
Yeah. All right. Now we are moving to the very important topic here. So this is why we have, so we will be usually building something to finally get a result, right? This is the final result for which we have studied what is eigenvalue, eigenvector, what is algebraic multiplicity, what is geometric multiplicity, what is the inequality. So all these things we studied for this result. Okay, what is this result? We are talking about what is mean by diagonalizable and why do we need diagonalizable. Okay, so very obviously, we have some advantages of a diagonal matrix over a regular matrix. For example, so this is some matrix. What are the eigenvalues we needed to compute? So if we have a triangular matrix, the computation process reduces drastically. But if we have a diagonalizable matrix, it reduces the process even more, right? So for example, this matrix is diagonal, the process has reduced a lot more. So what is that you see? First thing is that a diagonal matrix has computationally a lot more advantage than a regular matrix, like with a lot of non-zero entries. We are just looking at a 2 by 2 case. In general, for your data which you are handling like 1000 by 1000 or even lakh by lakh matrices, you have to handle. So imagine if you are having so many non-zero entries, it's going to make your life difficult. So you have to do too much. You have to spend too much on computations, right? But if you are able to have make it as a diagonal matrix, then what it can reduce the number of computations so effectively. So that's the first thing why we are looking at diagonalizable operators. What does mean by diagonalizable? It is not actually diagonal, but we can represent it with a diagonal form. That is what is diagonalizable. Diagonal means they are already diagonal. You don't have to do anything to make it diagonal. They are already diagonal. But diagonalizable means they are not diagonal, but we are going to do something to make it diagonal. How are we going to do that? We'll see now. So a linear operator is said to be diagonalizable if there exists a basis with respect to which the matrix of that T is diagonal. Okay, for example, maybe I will do with the start with an example. So the problem which we did today, T of x comma y is x plus y comma 2y. Right? What are the eigenvalues we have seen? Just go
1,
back
2.
1 and 2, and the eigenvectors are 1 0 and 1 1. Okay, so let us take this one. So lambda 1 is 1, lambda 2 is 2, and v1 is 1 0, v2 is 1 1. Is this correct? Yes. Okay,
Yes, ma'am.
now I want to write the matrix of T. So we know that this forms a basis now, right? So let's call this b1 and this is b2, the canonical basis. The matrix which we usually find is the canonic matrix with respect to the canonical basis 1 0 and then 1 2.
1, 2.
So this is with respect to the canonical basis. Now I want to do the same with b1. Okay, so I want to find the matrix let's call it some other name. So maybe I will call it B, be the matrix of T with respect to B1. What does it mean? I want first column is TV1. So column 1 is TV1 in terms of V1 and V2. Similarly, column 2 is TV2 in terms of V1 and V2. So what is TV1 definition? Lambda 1 V1, right? So here in this case it is lambda 1 is 1, so simply V1. So the coefficient of V1 is 1 and coefficient of V2 is 0. Now what is TV2? According to definition, it is lambda 2 V2 and lambda 2 is 2 and coefficient of V1 is 0 in this case. Okay, so now what is the first column? Can you tell me? Column 1 TV1 in terms of the coordinates of TV1 in terms of V1 V2. Similarly, coordinates of, so what is the first column? What are the coordinates of TV1?
1 0
Yes. And what are the coordinates of TV2?
1
2
1.
2.
Yes,
0,
ma'am. 2 2.
0 and 2. Now is this diagonal?
Ma'am, V2 is 1 1, right?
V2, see, I'm telling coordinates of TV1 in terms of V1, V2. That's why I wrote it. So these are the coordinates. 1 and 0 are the coordinates of TV1 in terms of V1 and V2. Similarly, coordinates of TV2 in terms of V1 and V2. Got it?
Yes, ma'am, but here in TV2 it is written 2V2 and V2 is 1 1, right?
No, no,
So,
no. What does mean by coordinates here? These coefficients of V1 and V2 are the coordinates. See, what do we do here in the case of canonical basis? TE1 is 1E1 plus 0E2. So 1 and 0 are the coordinates. Similarly, TE2 is 1E1 plus 2E2. The coefficients are the coordinates.
Okay, ma'am. So
oh,
we are
okay, ma'am.
not
Yes,
taking
ma'am.
the vectors V1 and V2. We are taking the lambda values of that is the coordinates of V1 and V2.
Exactly. This is the usual
Okay.
matrix representation concept. Okay. So here you see that the coefficients are the coordinates here. Okay, so you see that when we are using this as a basis and we are expressing this transformation with respect to this basis, the matrix is now diagonal.
Ma'am, this A is the coordinates of TV1 and TV2, right?
Which one?
A matrix 1 0 are the coordinates and
1, 2. So this is like coordinates of T1 and T2 in terms of E1 and E2. This one.
okay, ma'am.
Okay. So now let's go back and read the definition of diagonalizability again. A linear operator is said to be diagonalizable if there exists a basis with respect to which the matrix is diagonal. Okay, so here we were able to find a by basis 1011 where we are able to express the given transformation as a diagonal matrix. Okay, so what is the condition which can guarantee us that we can have such a basis? A linear operator T is diagonalizable if and only if there is a basis of eigenvectors. So if the eigenvectors forms a basis, then we can diagonalize. Okay, so it means what? We need at least two linearly independent eigenvectors. Okay, so this is the definition and the condition. So the first one is the definition and this is the condition. What is the condition? We need a basis of eigenvectors. This is a condition. What is the process of diagonalizing? Okay, so the process of
Excuse me.
yes,
When we say we need a basis that spans the entire domain. Is that what is meant?
yes, basis consisting of eigenvectors, basis of R2. We are talking about basis of R2. Okay.
So domain only, no, or something else?
See here, diagonalizability, we always talk about Operators. So talk for operators. So domain or codomain both are same in this case. Okay, diagonalizability is for operators. So domain and codomain are same. So either if say
Uh,
domain or codomain, it doesn't matter. So the underlying matrix is a square matrix. So you are talking about the size of the matrix here, or Rn in general. Okay.
sorry, this is kind of this may have been covered long ago, but we are only dealing with square matrices here in this whole eigenvalue, eigenvector discussion.
Exactly. Exactly.
So we call it operator when it is applying onto square matrix.
Yes, when both the domain and codomain are same, we call them operators.
Okay, and the word transformation is used when it may be different also.
Yes. Yes.
Okay, thank you.
Yeah. Okay. And how are we going to diagonalize a matrix? Okay, to diagonalize a matrix A, we need to find a matrix P, the matrix of eigenvectors, and a diagonal matrix D such that A equal to PDP inverse. Okay, what is this A equal to PDP inverse? Let us see it with the example which we have already done. Okay, so what is your A? This is your A. Okay, and this is your D. Okay, what is your P? Your P is nothing but V1, V2. What is V1? 1, 0. What is V2? 1, 1. Why always P inverse exists? Because V1 and V2 are linearly independent. I know P inverse is always there. P inverse is always defined. Can you all quickly compute what is P inverse? Compute and tell me.
1 minus 1 0 1.
Yeah. Okay. So now what is the formula given to us? The formula we have is that A equal to PDP inverse. Shall we verify whether we are getting that? So here PDP inverse. Everyone do the computation. What is P into D? First calculate this and tell me. 1101 1002. Calculate this and tell me. What is the first row? First column? 1
1 and 0.
0. What is the second column?
2 2.
0 2.
It's 2 and again 2. Correct? Okay. It's 2 and 2.
Yes, ma'am.
Now what is PD? P inverse. That is 1202 into P inverse, which is 0 minus 1 0 1. Now what is this? The first
0.
0. Are we making any errors? It should not be 0.
P inverse is the
1 1.
So in that case, the first entry is 1.
1.
And then you have minus 1 plus 1. So again 1 and then 0 0 here 0, and then here you have 0 plus 2, so 2. Is this equal to A? So did we get A equal to PDP inverse?
Yes, ma'am.
So do you understand the process of diagonalization? We first find the eigenvalues, find the eigenvectors and the matrix representation of T. Okay. Now then what we do? We find the diagonal matrix D. What is D? Your D is nothing but always lambda 1, lambda 2 is your D. Okay. And your P is nothing but V1, V2. First column is V1, second column is V2. That's all. Nothing much. So let's see it with another example here. What are we doing? Suppose this is the matrix you are given. You first find the eigenvalues. Once you find the eigenvalues, you find the corresponding eigenvectors. Okay, and write them as a matrix P. So the first, this is V1, this is V2. This is lambda 1, this is lambda 2. So we formed PD. Then you can find P inverse from here. Okay, and then so maybe I will leave it as a homework. Find P inverse and verify A equal to PD P inverse. Okay.
Excuse me, ma'am.
Yes.
Ma'am, this is same like we did earlier, the with respect basis changes. Is it like that?
No, basis change is a little different. Yeah, it looks similar, but it is a little different. Basis change is a little different because here the matrix, the diagonal matrix D, yeah, it is a matrix representation with respect to a different basis. So the comparison is very correct, but only difference here is that here this basis which we are obtaining is from eigenvectors, and the matrix we are getting here is the diagonal matrix. That is the only difference. But this process is exactly similar to the, or in fact the same as the diagonal basis change process, because here A is a matrix of the same transformation with respect to canonical basis, and D is also the matrix representation of T with respect to another basis. Yes, process is exactly similar.
Also, one more question. We are multiplying this D in this matrices. So, isn't like we are changing the real matrix? Because if we are multiplying something, we have to divide it also. So, if we are multiplying D by our own, so we have to divide it also, right?
I don't understand what.
We are making one matrix as diagonalizable, so we are multiplying this D, right, ma'am? And if we are multiplying this D, so aren't we changing the real x and y?
Okay, so what you have to see is that A equal to PDP inverse. This form, okay, so this form, why there are some properties lost when we are, so suppose let us say I want to look at the matrix D as a representation of A. Some information is lost in D, that is what you are talking, right? So this D does not contain all the information exactly similar to that of A. That is what is your concern, right?
Yes, ma'am.
Okay. So the thing is that yes, there are some property loss, but some important properties are preserved. What are those important properties? So for example, here your matrix A, it is 4 1 2 3, right? It is 4 1 2 3. What is trace of A?
7,
Okay. What is determinant of A?
10,
10. What is trace of D?
7,
What is determinant of D?
10,
Okay. What are the eigenvalues of A?
4, 3. But
No, 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 no. The
we have
eigenvalues
to find it.
5 and 2, right? So for both of them, lambda 1 is 5, lambda 2 is 2. These are the eigenvalues. Eigenvectors and eigenvalues are same. See, you see the essential properties are preserved, and that is enough. So D is the diagonal form for A, and all these properties are preserved. You see the beauty here. So all these important properties are preserved in this diagonal form. And now instead of considering this matrix, I can consider this matrix for several important applications. One such application is the power of a matrix. So if you all understand how to diagonalize a matrix, then we can move to the next step. Are there any questions so far?
So, ma'am, we cannot use this eigenvalue thing on real matrix, real linear equations.
Sorry, I don't understand your question.
Because we can now use this diagonalizable thing in real linear equations, means we are changing the x and y values then.
I still don't understand. So you are saying, okay, so are you saying that the transformation corresponding to A is different from the transformation corresponding to D? Is that what you are asking?
No, in the starting you said na ki the linear equations we can solve, make it easy, and we can get x and y thing. So if we just do this diagonalizable thing,
Hmm.
so we will lose the correct value of x and y while solving the big matrices.
No, no, no. See, here, what is the underlying linear transformation is not important. For us, there are some other important things which we need in applications where this diagonal matrix is useful. Okay. So, what you are saying is that the underlying transformation, we cannot, like, if you are doing the XY, then, for example, the null space and the range space, they are different for this and they are different for this matrix. There are several different things which are changing, but the essential things, certain things which we need to be preserved in applications are there, and one such thing where you see this D is going to contribute is powers of a matrix. Yes, there are some changes. Yes, definitely A and D have some properties which are different. But that is our least concern, because you see how it is going to be useful for us. So you take a matrix A, okay, and let's say lambda 1 and lambda 2 are the eigenvalues. Okay. Now, if lambda 1 and lambda 2 are two distinct eigenvalues, okay, so in that case, you know that you have an diagonal representation for this. So you can find an invertible matrix S. So where S is the eigenvectors corresponding to lambda 1, lambda 2, right? And now, how do you compute the powers? Imagine computing powers of a huge matrix. Now we are having just 2 by 2. Even that involves quite some computation. But now, once you have this form, what is A square? A square, you see, S times of D S inverse into S times of S. So A square is SD S inverse into SD S inverse. Now I am going to rewrite it as SD S inverse S D S inverse. S inverse S is identity. So this I can simply write it as S D square S inverse. Okay, so this is D square. So if I do this process repeatedly for any A power n is S D power n S inverse. So computing powers is much easier if you have this. Okay, and there exists an invertible S such that, so here if it is non-diagonalizable, then you have an upper triangular form. For 2 by 2 case, you have an upper triangular form like this. You can find, so let's say this is your, so your S is again here V1, and here V2 is some extended basis. So you know basis extension property, right? If you have one element, then how to extend the basis, that we have seen in previous weeks. So if V1 is an eigenvector, V2 you are finding some vector where you are extending the basis, extending it to form a basis, and with that you can find an upper triangular form. Okay, and there is one important thing I want you to
Not
know.
an eigenvector.
V2 is not an eigenvector in this case, because here it is non-diagonalizable, right? We will have only one linearly independent vector corresponding to this. So in this case, so algebraic multiplicity is 2 and geometric multiplicity is 1. So another important thing for diagonalizability here is that, let me write it in red. So algebraic multiplicity of lambda equal to, let's say lambda I equal to geometric multiplicity of lambda I for all I. Maybe I'll write just for all. For all I, if and only if A is diagonalizable. So we can diagonalize only if I have this condition. If they are not equal, then you know that it is not diagonalizable. If algebraic multiplicity is not equal to geometric multiplicity, then it cannot be diagonalizable. Okay, and the other important note which I wanted you to observe is that, okay, let us say that you are having, suppose A is a 2 by 2 matrix with eigenvalues lambda 1 equal to lambda 2 equal to lambda, both are same. Okay, and is it possible to find D, or let's say P, such that A equal to PDP inverse, where D is equal to lambda 0 0 lambda? What is your guess? Just do a wild guess. Let it be right or wrong, don't worry. What is your random guess? Yes or no? What is the answer?
Ma'am, no.
No,
No, ma'am.
no, right? Why it is no? Because see, also another assumption I need here. Let's say A is non-diagonal. Already I have this condition that A is non-diagonal. Okay, so now what happens? A is equal to, so what happens to PDP inverse? First let us see. So PDP inverse is nothing but, so P times of lambda 0 0 lambda P inverse, which is lambda times of I P inverse. If I take lambda, then this is just the identity matrix, right? This is lambda times of identity. I can take the lambda out. So this is lambda times of PP inverse, and PP inverse is again identity. So this means that this is just lambda 0 0 lambda, and this is not equal to A. It is not possible. So not possible. Okay. So this is something you should know. So for a 2 by 2 matrix, okay, to be diagonalizable, you need distinct eigenvalues. Otherwise, it is not diagonalizable. Is it clear? Okay.
Yes, ma'am.
Okay. Now, from the powers of the matrix, how do you compute the powers? Here, you already have computed A equal to PD P inverse. So, compute it using the PD P inverse you have used. So, this also I am leaving it as a homework. Just some computations only. There is nothing for me to explain here. Just doing matrix multiplication. So what are the things we have seen today? What are eigenvalues and eigenvectors? We revised what are eigenvalues and eigenvectors. Then we saw some important properties. So distinct eigenvalues gives distinct or linearly independent eigenvectors. And then we saw that product determinant is the product of eigenvalues. Trace is the sum of eigenvalues. And because of this, a matrix is invertible if and only if it has non-zero eigenvalues. And then we introduced what is algebraic multiplicity and geometric multiplicity. Algebraic multiplicity is the number of times an eigenvalue is repeating in as a root of this polynomial. And geometric multiplicity is the number of linearly independent eigenvectors we can find with respect to a given lambda. And the inequality for them is 1 less equal to geometric multiplicity less than or equal to algebraic multiplicity less than or equal to n for an n by n matrix. Okay, and based on this we saw what is diagonalizability. Diagonalizable means if you are able to find a basis with respect to which the transformation is diagonal. So what is the condition for diagonalizability? Algebraic multiplicity should be equal to geometric multiplicity. That is the condition for diagonalizability. And how do we diagonalize? So if we have a matrix A, we find the eigenvalues and eigenvectors. Once we have the eigenvalues and eigenvectors, we form the matrix P and D in this way. P is V1, V2 and D is lambda 1, 0, 0, lambda 2, and then you have A equal to PDP inverse. Okay, so these are the things we have covered, and based on this you can find A power n is equal to SD power n S inverse. So these are the things we have seen in today's session. Are there any questions?
Yes, actually, a lot of questions.
Yes.
Do we have time for the questions?
Yes.
Yeah. When we go to the diagonalization thing,
Mm.
we wrote that formula PDP inverse, but what is it really saying? Can you just go back to where you had written it out? No, where you had actually shown the transformation in terms of the vectors and stuff.
This one?
Right here. This one. Here we managed to start off writing D. When we wrote D, we expressed it as this C1 and C2. Can you please go over again how we got this C1 and C2?
Okay, so what is the concept of matrix representation? First of all, this is nothing but the concept of matrix representation. How do you, so let us say you have some basis V1 and V2. Okay, and you want to express a transformation T from R2 to R2. Okay, so find M of T with respect to beta, this basis B for both domain and codomain. If you understand this question, then the other thing will follow. How do you do this? How do you do this? For this, you find TV1, okay, and whatever you are finding, you express. Now this is a basis, so express it as, let's say, A11 V1 plus A21, or maybe I'll just put alpha 1 beta 1. Let's not confuse. So alpha 1 V1, alpha 2 V2. Similarly, TV2, I can write it as, let's say, beta 1 V1 and beta 2 V2. Now, what is this matrix I need to find? The matrix I need to find is simply alpha 1, alpha 2, beta 1, beta 2. This is the way you find matrix with respect to the same basis for both domain and codomain. Now there is another question also based on this matrix thing. So suppose I'm asking, suppose let us say I have another basis, let's say beta 1 and beta 2, suppose I'm having, and suppose u1 and u2 is this basis and v1 and v2 is another basis. Now how do you find matrix of T with respect to beta 1 for domain and beta 2 for codomain? How do you do this? In this case, you write TU1, okay, equal to alpha 1 V1 plus alpha 2 V2. You find TU1 and express it as in terms of V1, because for domain you need to take from beta 1 and for codomain you need to take from beta 2. So TU2 is alpha 1 V1, sorry, beta 1 V1, beta 2 V2. So in this case the matrix is alpha 1 alpha 2 beta 1 beta 2. So this is the general process of finding matrix with respect to different bases. Okay, so here in this case we are considering the same basis for both domain and codomain. You can in fact do it for different bases also, but for diagonalizability we are only concerned with same basis for domain and codomain. Now if you look here, do you understand? We are just finding the matrix representation of T with respect to the basis consisting of eigenvectors for both domain and codomain. Now the process of finding C1 and C2, is it clear for you?
Can we just write the original matrix alongside, please?
It's here.
That is V1 and V2, right? Or is that the matrix of the transformation itself?
This is the matrix of T with respect to the canonical basis for both domain and codomain.
Right, that is the original matrix.
Yes.
And then V1 and V2, where do we have those separately? Do we have them anywhere?
Yes. So this is V1 and V2, and TV1 is 1 V1 plus 0 V2, and TV2 is 0 V1 plus 2 V2. And the coefficients I have written here.
Alright, so how did we get 1 V1 plus 0 V2, please?
Because TV1 is lambda 1 V1 and lambda 1 is 1. So it is 1 V1 and there is no coefficient for V2, so it means 0 V2.
So lambda 1 alone is enough, combining with V1.
Yes.
Okay. And in the second one, we put in the value of lambda 2 equal to 2.
Yes.
And then we said that lambda 1 is not needed because lambda 2 V2 is alone enough.
Yes, yes.
And then we took those coefficients 1, 0 and 0, 2 and put them as the columns of D.
Yeah, yeah.
So that the columns of D are basically just eigenvector value multiplied by its respective eigenvector, and we put it over there.
I don't think this way of saying it is correct. We should say that D has, the columns of D are the coordinates of v1 and v2, v1 and v2 in terms of v1 v2. That is how we should say the coordinates of t v1. First column is the coordinates of t v1 in terms of v1 v2. Second column is the coordinates of t v2 in terms of v1 and v2.
But in the PDF, ma'am, you have just formed the matrix D, putting the eigenvalues along the diagonal. In the upper, scroll it up, please. Uh, there, just you have here you form the matrix with the eigenvalues. Can
See
we
the
allow to do this way also?
see the I have just explained the background of this d. So the d, how did we get, what is the background? It is this. So lambda 1 lambda 2. See, this is a general scenario, right? See here, if I just write it as lambda 1 v1, then this is how automatically you are going to get. See, always you are having t v1 equal to lambda 1 v1, right? And t v2 equal to lambda 2 v2. Whenever you are having distinct eigenvalues with linearly independent eigenvectors, you have this condition. Now this I can write as lambda 1 v1 plus 0 v2, and this I can write as 0 v1 plus lambda 2 v2. And so the matrix here is, for what are the coordinates of t v1 with respect to v1 v2? Lambda 1
Lambda
0,
1 0
and
and
for
0
t,
lambda 2.
that's all. I have
Ma'am,
just
Okay, this is,
explained
ma'am,
the reason
that
behind it.
that I understand. This is a general scenario, but can we allow to write the directly matrix D with the values, eigenvalues?
Yes, that's what I have explained just now. Whatever is the
Oh,
eigenvalue, if you are following the process or not, the final resulting matrix is this.
okay, got it, ma'am.
ma'am, it's more like we are finding it in canonical basis, but we are just multiplying by lambda 1 and lambda 2.
No, we are not find you. We are not at all using canonical basis here. No. Okay.
Okay.
We have used the
Ma'am,
basis v1 and v2 only. We did not use canonical basis here. No.
excuse me, ma'am.
Yes.
One question, please.
Yeah.
The last question you gave us a homework, that is a to the power 5, right?
Yes.
This one. So it is mandatory to follow all the procedure first to find the eigenvalues, then eigenvector, then
Yes.
P matrix P and matrix D, and then form the PDP inverse. Then see the pattern and write the powers of A.
Yes. Exactly.
Can we can't we allow to directly, if here let's say A to the power 100, so
Hmm.
can we allow to do suppose A into A, then A4, then we can see the pattern and write the directly A to the power 100?
But do you think always there is a pattern for the powers of a matrix?
Yeah, not always.
Hmm.
Okay, ma'am. So it's not always, that's why we are following this procedure.
Yes. Correct.
Okay, thank you, ma'am.
Yeah. Any other questions?
Coming back to that PDP1 inverse formula,
Hmm.
um, what we are really writing is that A multiplied by P will be equal to P multiplied by D.
Yes.
So if we think about it in terms of linear transformations,
Hmm.
let us look at the right hand side, which says PD.
Yeah.
Here we are saying that there is some transformation matrix D. This is in some sense transforming our canonical basis vectors. In what way exactly? Is it making new canonical basis vectors? Because it looks very similar, as somebody mentioned.
Canonical basis is the name for 1001. We are giving the name canonical basis for specifically this vectors. Okay. Now, what is that this is doing? You don't have to think in the way like A, P, and D, P, D. You don't have to think it that way. See, we call, if forget about this diagonalizability. In general, if we have something like this, A is equal to PBP inverse, then we say that A and B are similar. This is a definition. So here we are making A similar to a diagonal matrix. Now A is similar to a diagonal matrix. Okay, so this is a definition we are not using in this course, but yeah, so what does this having, what does this say is that use the determinant properties. If we are using the determinant properties, determinant of A is same as determinant of P into determinant of B into determinant of P inverse, right? And then again you further split the determinants. What will you get? Determinant of P, determinant of B, and how can we write determinant of P inverse? 1 by determinant of P. So this will get cancelled, and then you see that determinant of B. Okay, so similar matrices have same determinant and same eigenvalues and trace, so everything as I mentioned earlier, and that's the essence here. So the same transformation, whatever is the transformation you are having, the final essence is that you are able to represent it as a diagonal matrix, and this diagonal matrix helps us to reduce some computations. That's the only takeaway you have from the diagonalization process. And also in the diagonalization process, you can split the whole basis or the whole space into smaller, you can decompose the entire basis into smaller subspaces, where each subspace is spanned by the individual eigenvectors. So just because we are looking at a 2 by 2 matrix, we are just having R2 and there is nothing much to visualize. So R2, you can say that it is the, you see the span of this and span of this, but whenever we are having a big space, and then you see that the entire space you can decompose into smaller spaces. For example, as I told you in this case, three case scenario, right? Where is that? Where was that example, the 3 by 3 matrix? Yeah, so in this case you see that the entire R3, I am able to write it now as this is the span of the null space and this is the span of the range space, where the intersection is empty, and this R3 is decomposed with these two spaces. So in this way, this diagonalization also helps us to decompose the entire space into smaller subspaces. So what is decomposition and all, let's not go into that. Just because you are asking what is the essence and what does this have to do with in general transformation, I have just given an outline. Okay, so don't worry about these things which I told you, like what is similarity, what is decomposition and all. Please, I'm telling to all of you, please don't worry about all these terms I told. Just because some student is asking more about it, I'm telling. For this course, don't worry about this term similarity and decomposition and all. Okay, fine. I
So here we focus on using the PDP inverse formula
Yes,
to reduce our computation. That is the focus over here.
exactly.
And all this background is simply to inform us that the PDP inverse formula works because of certain reasons. Those reasons are not immediately important. We need to use this formula to do our work.
Exactly.
Okay, thank you.
Yes. Okay, are there any other questions?
Actually, ma'am, just we have to check the conditions that the vectors, eigenvectors are linearly independent, and then to compute the power, we have to just make the power of lambda. That is our task, na, sir?
That's all. Okay, compute the eigenvalues, compute the eigenvectors. If they are spanning the entire space, then just write them as columns of a matrix, which is P, and then write the entries of the eigenvalues in the diagonal of a matrix and call it D. Then compute A equal to PDP inverse. That's all. Okay, fine. Okay, so I hope this session was useful for all of you. We will see in another session. See you all. Bye.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Ma'am, where can we get this PDF?
As usual, in the drive, um, the usual